Good afternoon, everybody. My name is Christine Hubbard, and I am the president of Academic Solidarity with Palestine. We are very pleased to host the fifth edition of these Gaza Excellence Talks with Dr. Edward Witten today. It is a great honor to have him. As you know, these talks are co-organized by our NGO, Gaza Academic Solidarity with Palestine, and more importantly, with Al-Aqsa University in Gaza. Unfortunately, Gazan universities and Al-Aqsa in particular are being systematically destroyed, and right now there's a huge internet problem. So the president and the vice president who were supposed to log in could not. However, asked us to hold this talk on their behalf and with them, because this talk is with and for Gaza above all. So let me thank all of you for being here today. It is immensely important. I would like to read a quick message from a colleague in Gaza who unfortunately could not join because his internet is not accessible. To everyone at the talk, I wish I could be there, but I cannot. I am writing to you from the heart of Gaza, a place that is being systematically destroyed. You want to talk about excellence, so I must tell you what that word means here right now. Excellence is a student trying to find their book in the rubble of their university. Excellence is a doctor performing surgery with no electricity. Excellence is a mother finding a piece of bread to feed her child. Everything here has been targeted by the IDF. Our hospitals, our schools, and our universities, like Al-Azhar and Al-Aqsa, which were hit several times. They are both gone. They are not just destroying buildings. They are trying to destroy our future. All of our people are targets, the young, the old, children, women. No one is safe from the bombs. They have made our life in Gaza a living hell. So my message is this: please do not forget us. When you talk about our achievements, please remember the price we're paying just to exist. Our true excellence today is our survival. Our spirit will not be broken. Please tell the world what is happening to us. So this is a message from our colleague in Gaza. Thank you again, Dr. Edward Witten, for holding this talk with us and with and for Gaza. I will now introduce Dr. Edward Witten as if he needed any introduction. Edward Witten is a professor emeritus in the School of Natural Sciences of the Institute for Advanced Study in Princeton. He is known for his work on quantum fields and strings, including applications to geometry. His awards include the Fields Medal, the Crafoord Prize, and the U.S. National Medal of Science, among others. Thank you very much again, Dr. Witten, for being with us today, and I will give the floor to you now. Thank you.
Well, thank you very much, Anne Christine, and thanks for this invitation. We all know how difficult the situation is now in Gaza, and I can assure you I wish I could do more to help than just give a lecture on black holes, which I know will offer little comfort in these difficult times. But I will today be telling you about some of the basics about black holes and how we know what we know about them. And as you'll see in this talk, what we know about them has greatly expanded in the last decade. So Einstein's theory of gravity, which was his greatest achievement, is called general relativity, and it was completed in November 1915 in another very difficult period in the world. Einstein was living in Berlin at the time. Of course, Germany had been engaged in World War I for over a year by the time Einstein completed his theory. Einstein never supported the war, and he had plenty of time to work on his theories while other people, unfortunately, were busy with the destruction of Europe. Now, when Einstein completed his theory, there were not very many people in the world who had the mathematical skills to understand what Einstein was doing or saying and try to develop it. One of the few was the astronomer Karl Schwarzschild. And almost immediately, Carl Schwarzschild discovered what we now know as the first black hole solution of Einstein's theory, although it took half a century for that understanding of Schwarzschild's work to emerge, to fully emerge. As I said, he was one of the few people with the background to understand Einstein's equations. He was old enough that normally he was exempt from military service, but tragically, when war broke out, he considered it his duty to volunteer for service at age 41. And his discovery of the black hole solution was done on the Eastern Front, where he soon fell ill and died in May 1916. But Schwarzschild was not trying to think about anything crazy like a black hole. By the way, I'm not sure how this image looks to you, but on my screen, a couple words are missing on the right because they're blocked by the images of myself and other people. Einstein was just trying to understand Schwarzschild was just trying to understand, in the context of Einstein's theory, the gravitational field of an ordinary body like the sun. And it took a long time before anyone really understood his solution. And it also took a very long time before anybody improved on Schwarzschild's work significantly. In fact, it was almost half a century before, or 47 years to be precise, before the next important discovery of a black hole solution. Roy Kerr, the astronomer from New Zealand, in 1963, discovered the solution of Einstein's equations that describes a rotating black hole. And since almost all black holes in the universe are rotating, this turned out to be an important advance. But it took a long time for anyone to take seriously the idea that Einstein's equations predict that a collapsing star can collapse into something as exotic as a black hole. And even then, when there began to be evidence that black holes really do exist in the heavens, the evidence was really indirect. For example, astronomers would see objects so heavy and so small that it seemed they must be black holes, because anything else you could imagine that would be so heavy and so small would be unstable and would soon collapse to a black hole. And sometimes these objects emitted huge amounts of energy, which could be explained by the gravitational field of the black hole. But the evidence that it really was a black hole was very indirect. Direct evidence was another matter. And in the last decade, that's changed, mainly for two reasons, but it's really only changed in the last decade. The two reasons are, first, that starting in 2015, the LIGO Observatory was able to detect gravitational waves from colliding black holes, sorry. The second was that starting in 2019, it became possible to take close-up photographs of the neighborhood of a black hole. The first such close-up was released in 2019 by the so-called Event Horizon Telescope collaboration. So each of these breakthroughs has turned into a major area of research, and a lot of work is done up to the present and beyond. And in the rest of the talk, I'm going to tell you about these two developments. First, the observations of gravitational waves from black hole collisions, and then we'll go on and talk about the close-up pictures of a black hole. Now, before starting to talk about observations, I'm going to show you a movie that's a computer simulation of two colliding black holes, and then we'll talk about what we've seen. So first of all, before I start the movie, in this picture, there are two black holes. I hope you can see my cursor here. So here's one black hole, here's the other. The black holes look like literally black holes in space. In this movie, we are about 1,000 kilometers from the two black holes, and they are a few dozen kilometers from each other. And what we're seeing are stars that are far more distant. And as will become clearer when we start to play the movie, the apparent positions of the stars are affected greatly by the gravitational fields of the black holes. But also, the black holes look like holes in space, roughly because if a star is precisely behind the black hole, the light from that star gets captured by the hole, and therefore there's a gap in space where we don't see anything. That's why it's called a black hole. It creates an apparent black hole in the image of the stars behind it. So we'll discuss that in more detail after we watch the movie. So you can see the black holes are orbiting each other. And as they orbit each other, you can see that the apparent positions of the stars are wildly moving as the black holes move around. And then the black holes are going to emit gravitational radiation, lose energy, and spiral in closer. And finally, they'll merge into a single black hole. So now the system has settled down. I want to show the movie again. So two black holes are spiraling around each other. They're gravitationally bound, like the Earth moving around the sun. The two black holes are moving around each other. But in Einstein's theory, they're emitting gravitational radiation. So does the Earth, but the Earth is so light that it emits small gravitational radiation. The black holes are radiating much more strongly, which causes them to lose energy and spiral inward. And as they move around, we see what's happening, not because we directly see the black holes, but because as they move around, it affects our ability to see stars behind them. So now we're going to discuss in more detail what we've seen. One thing we notice is that black holes do look like holes in space, like black holes in space. That's because they block light coming from behind. Here I've drawn a schematic picture. I'm not sure what happened to my cursor. A moment ago, we had the cursor. Now, why does it go away? Okay, I don't have the cursor to show you, but in the center is a black hole schematically. On the right, I've drawn the eye of the observer. That's us trying to look at things. And on the left, very schematically in red, is a star, and we're trying to observe the star. But a light ray coming straight from the star to us meets the black hole, which captures it. The light ray doesn't emerge, so we're not able to see the star behind the black hole. However, that doesn't mean that we're not able to see the star behind the black hole. We see it because of the way light is bent by the gravitational field of the black hole. Here's the same picture again, but now I've drawn a light ray that leaves the star in the upwards direction. But in the field of a black hole, a light ray does not travel what you'd naively regard as a straight line. Its path is curved in the gravitational field. And in this case, the light ray going above the black hole reaches the eye. So we will indeed see the star that's behind the black hole. But the bending of light means the apparent position of the star will not be where it really is. I put the words really in quotes because as one learns if one studies Einstein's theory, there's some subtlety about what you mean by what's really there. But anyway, the observer at the position of the eye on the right of the picture, seeing the light ray arrive, and I've drawn it in this picture in brown, will infer an apparent position of the star, which will be up here, shown up above on the left. So the observer will indeed see the star, but it will appear to be way up above its actual position. So you can see matter behind the black hole, but it will not appear to be behind the black hole. Now I've explained this as if we see just one image of any star, but actually we will see multiple images of the same star. This is most obvious if the star is symmetrically placed. Here I've shown that a light ray from the star on the left to the eye on the right can go above the black hole and be bent to the eye, or can go below the black hole and be bent to the eye. So that will give two images. But with a little imagination, you might be able to see that if you have a spherically symmetric black hole and a star behind it, and you're on the other side over here, a ray can go around the black hole in any direction. So you'll actually see a ring known as an Einstein ring. A star symmetrically placed behind the black hole will show up to the observer as a ring that surrounds the black hole. So I'll discuss later what we have in terms of pictures of black holes, but actually our best Einstein ring picture shows an Einstein ring caused by a galaxy bending the light rather than a black hole. And this is the picture. So in the center of the picture, and again, I'm sorry, the cursor, I think, isn't showing up. Well, this is a very atypical picture taken by the Hubble Space Telescope. It shows an almost perfect Einstein ring. At the center of the picture is this yellow galaxy. This yellow spot in the center is a bright galaxy that's a few billion light years away. But the blue ring around it, and it's almost a complete ring, is a picture of a more distant blue galaxy that is almost perfectly behind the yellow galaxy. But the bending of light has distorted the image of the blue galaxy so that it appears as an almost perfect ring behind or surrounding the yellow dot. Part of the ring is missing at the top because this isn't a perfect arrangement, but it's an almost perfect arrangement, producing an almost perfect Einstein ring. This is a very exceptional picture. A more typical Hubble picture looks like this. You see a lot of yellow spots that represent galaxies, and if you look closely, you'll see a lot of arcs. Like there's an orange arc in the center. Again, I'm not sure why my cursor isn't showing up, so I can't highlight it. But there's an orange arc in the center of the picture that's actually a much more distant galaxy whose image has been bent into a partial Einstein ring by the gravitational field of the yellow galaxies. And if you look closely, you'll see a number of other arcs, most of which are bluish, and they represent the bending of light from a more distant galaxy. Now, we're going to look at the movie one more time, but first we'll discuss a few basic things. So first, the two black holes at the beginning are orbiting each other a little like the Earth orbiting the Sun. But as the Earth orbits the Sun, it's accelerating, and Newton's laws describe that the gravitational force produces that acceleration and keeps the Earth in orbit. But in Einstein's theory, as they accelerate, they emit gravitational radiation, which ultimately was detected on Earth, as we'll discuss. As an orbiting body emits radiation, it loses energy, and the orbit becomes tighter and tighter, and it spirals in, and eventually the two black holes merge into a single black hole. As they move around, the star field behind them is greatly distorted by the bending of light by the black holes. So here's the movie that we watched before, which we hopefully understand in a little bit more detail now. So the black holes are orbiting, spiraling inward, slowly at first, but in a moment they'll start spiraling very abruptly, and now they merge to a single larger black hole. Now, a basic thing we see in this movie is that light is deflected by gravity. And we also saw it in the Hubble picture showing the arcs and the Einstein ring. But why is that true? Well, Einstein actually guessed that light is deflected by gravity before he had fully invented his theory. He knew that a comet or a planet is deflected by gravity, so he thought it would also happen to light. Since Newton's day, scientists had known that the deflection of an ordinary body, for instance, a comet, by the sun depends on its velocity. Here, schematically, red depicts the sun, and in blue, I've drawn the trajectories of a slow or fast body moving past the sun. The fast body is deflected less, the slow body is deflected more by the gravitational field of the sun. So before Einstein had his theory, he just guessed he should use Newton's formula, which depends on the velocity of the body, and replace the velocity with the speed of light. So in 1911, Einstein guessed that the same effect would hold for light, using the speed of light in Newton's formula. So he made a prediction of the deflection by light. The effect was so small it could only be observed during a total eclipse of the sun. You wanted to observe the effect by looking at a star that was whose apparent position is very, very close to the sun, and its apparent position would be modified. As the Earth moves, the sun passes in front. The sun, as seen by Earth, appears to pass in front of a star. And the apparent position of the star would be modified as the sun comes closer, according to Einstein's prediction. But normally, daylight keeps us, even as astronomers nowadays, from seeing a star very close to the sun. The very, very bright light of the sun keeps us from being able to see nearby objects, even with modern telescopes, normally. But during a total eclipse of the sun, when the light from the sun is blocked out, you could hope to observe it. It's still a difficult observation because of the solar corona, but you can hope to observe it during a total eclipse. And Einstein was lucky, though at first it looked like bad luck. In 1912, people tried to test his idea in Brazil, but it rained. They couldn't see the eclipse. And then they tried again in Russia in 1914, but World War I broke out and prevented the astronomers from being able to make the measurement. So for several years, what looked like bad luck kept people from being able to test Einstein's prediction. In 1915, Einstein finally developed his theory, and it became clear that the Newtonian formula that he had guessed was 2 times too small. If his original prediction had been tested, well, it was wrong, so it might have caused a lot of confusion. But it hadn't been tested, and he came out with the modern prediction that was 2 times bigger. After the war, science resumed, and the eclipse expedition of 1919 confirmed Einstein's prediction. This was actually the event that made Einstein famous, that made Einstein a household name. Here's how the New York Times reported the event on November 10th, 1919. Light all askew in the heavens, men of science more or less agog over results of eclipse observations. Einstein's theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more in all the world could comprehend it, said Einstein when his daring publishers accepted it. Well, we won't fact check this in too much detail, but it gives you the idea of the impact that this observation had. I'll only say that the last remark, that no one could comprehend it, was an exaggeration, since, for example, as I told you, Karl Schwarzschild, within a year of the development of Einstein's theory, had discovered the first black hole solution and then had tragically died in World War I. So there were people who could comprehend it, but not too many. So this was a mild observation, a mild exaggeration. Nowadays, we understand Einstein's theory better. We're better at explaining it, and certainly we succeed in teaching it to students at universities around the world. Well, what was Einstein's theory? Einstein's theory was based on reinterpreting gravity in terms of the curvature of space-time caused by mass. Now, it's space-time, not just space, which is curved. And space-time is four-dimensional, and I can't really draw pictures of curvature in four-dimensional space-time. So any picture I can offer you is highly schematic. Here from Wikipedia is a picture which shows curvature in 2 dimensions, and the Earth is visualized as a weight on a trampoline, or uh, an elastic body like a trampoline or just a sheet of rubber. And the Earth weighs down and causes the 2-dimensional surface to be curved. That's really a cartoon version of Einstein's theory at best, but it will give you some idea. And now if you think about a marble rolling on this curved surface, you'll see that the marble will actually tend to bend toward the Earth. As it moves past the Earth, it will be deflected toward the Earth, and if it's moving slowly enough, it will go into a bound orbit around the Earth, like the moon orbiting the Earth. So although this is a cartoon, it does reproduce some aspects of how in Einstein's theory, curvature affects the motion of moving bodies. So when we think about a black hole, we should think of a highly curved region of space-time. What I'm going to show next is another movie of the LIGO event, which tries to help us visualize how space-time is curved, as opposed to showing what we would see if we were nearby, which is what the first movie showed. So here, in this picture, well, at the upper left, there's a display of the time. So it says minus 0.76 seconds. So this movie is going to start 0.76 seconds before the black holes merge. And then what is schematically shown at the bottom is the signal of gravitational waves that come out of the event. And before we start the movie, you can see that there are very faint spirals in blue surrounding this event at big distances. Oh, now I can highlight them. So for some reason, my cursor works now that we're at a movie. So here you can see very faint blue spirals surrounding the event. Now in the center, The black dots represent the black hole. And the people who made this movie have tried to convey the idea that the black dot is creating curvature in space-time. So what's really there is the curvature, which we're going to zoom in on in a second. You can't see it well right now, but the orange-yellow spots here are highly curved regions of space-time created by the black holes. The black dots in the picture you should think of as not being really there. They're there to guide the eye, to tell us what are the curved regions of space, but what you're really supposed to look at are the curved space-time regions below the black dots. But the movie makers were only able to show curvature in space. Curvature in space-time, no one has imagined how to capture it in a movie. So what's really happening in Einstein's theory is subtler than this movie can show. But anyway, we'll take a look at this movie. So the black holes are orbiting each other, getting closer. I'll stop the movie if I can, yes. So the black dots are closer, and now you can more clearly see that there are dips in space. And the dips in space are what are really the black hole. So the Schwarzschild solution shows us that in the presence of what we now call a black hole, there's a dip in space, this drastically curved region where space dips. Unfortunately, space dips, but it's hard to explain what space-time does, which is the full story. So here there are two dips in space that are orbiting each other. Again, the black dots are only to guide the eye, and you can see the purple ripples going out. And now we'll continue the movie, and the dips in space will spiral in, get more pronounced, and eventually merge. So now we're 0.46 seconds before the merger. And the arrows are meant to suggest that if you're nearby, you maybe would be sucked down the hole by the gravitational force. So the space-time geometry gets more and more deformed as the black holes orbit and get nearer. And now they slow down the movie so you can see more better the last stages. So the two dips in space are merging into one. And there's this crazy peak. It's highly, okay. Then it settles down. So space was very distorted at that peak, but now it's settled down to a single black hole, and now they're zooming out so you can see the outgoing shells representing outgoing gravitational radiation. So at the end of the movie, you saw the outgoing ripples that represent the gravitational waves. Well, why does that happen? Well, if I move an ore in the water, I create water waves. If I take an electrically charged body and shake it, I create electromagnetic waves, which become radio waves or waves of visible light, if the shaking is fast enough. According to Einstein, if I shake a mass, I create gravity waves. But Einstein and his contemporaries thought this fundamental prediction of his theory would never be tested because gravitational waves interact so weakly. So when Einstein predicted gravity waves, the prediction seemed like science fiction. Einstein and his contemporaries did not anticipate the technology, especially laser technology, that made LIGO, the detection of gravitational waves, possible. They also did not anticipate the existence of such powerful sources of gravitational waves as the merger of two black holes. I'm going to show another movie that emphasizes the gravitational waves that came out of the LIGO event. So in this movie, again, the black dots represent the two black holes, and you can see in green very weak ripples in space that have been created by the orbiting black holes. But as the black holes draw closer, those ripples will become stronger. So the black holes are orbiting. They're creating these outgoing ripples in space, which at this stage are too weak to be detected on planet Earth with our present technology. But they're going to get stronger as the black holes orbit and get closer. And the very final stages were then detected, of such an event, were then detected by the LIGO detector. So how strong was the gravitational wave created by this event? Well, there are different ways to measure that, but I'll say it first in one way. This symbol that I've written here, a capital M with that funny symbol next to it, this symbol represents the sun, and M with that symbol represents the mass of the sun, about 10 to the 33 grams. The black holes that merged in the LIGO event had estimated masses of 29 and 36 times the mass of the sun, but the final black hole had an estimated mass of 62 times the mass of the sun. So a mass 3 times the mass of the sun disappeared in gravitational waves. So that's a very, very vast energy, 3 times mc squared of the sun, disappeared in gravitational waves. All that mass was converted into gravity waves. So the energy of the gravitational waves was 3 times mc squared, where m is the mass of the sun. About 1 billion years later, the gravity wave arrived at Earth. And here's a cartoon of what happened. But I have to warn you, it's a cartoon. If shown to an audience of physicists, this cartoon often produces laughter. It's highly exaggerated. A gravity wave passing through matter will cause the matter to vibrate, to start to oscillate. And the person who made this movie, as you can see at the bottom, it says scale of effect vastly exaggerated. The Earth was set into very, very slight vibration or oscillation by this passing gravitational wave. But a movie was made that, for perhaps comic effect, vastly exaggerated the effect. So here you can see in green the gravity wave. Schematically in green is the gravity wave. The passing gravity wave causes the Earth to start vibrating. And in this vastly exaggerated cartoon version, the Earth is set into wild vibration. In reality, the vibration was so weak that it took incredible effort with modern technology to detect it. It was seen by the LIGO Observatory, and here's a picture of the LIGO Observatory, or at least the LIGO Observatory has 2 detectors a couple thousand miles apart. The reason for having 2 detectors is that they see a very slight signal, which could be simulated by anything. A local seismic wave, a passing truck, anything could cause a vibration in the detector that conceivably could fool you into thinking you'd seen a gravitational wave. So to be sure, they had 2 detectors 2,000 miles apart, several thousand kilometers apart, and they made sure that they detected simultaneously the same thing at the 2 detectors. So anyway, here's a picture of one of the detectors in the desert in eastern Washington state. And again, my cursor isn't working, but near the center of the picture, you see the laboratory itself. And then there are 2 arms, these white rays that go off into the desert for several kilometers each. And um, a laser beam is sent from the central detector, bouncing up and back in each of the 2 arms. So the laser beam travels a few kilometers forwards and back, and it's adjusted so that the 2 arms have precisely the same length if the gravitational wave doesn't pass. But when the gravity wave passes, it slightly disturbs the distances so that the 2 arms are not exactly of equal length. And that's what's detected by an interference effect between the 2 oscillating laser beams. And here's the signal as it was detected in Hanford, Washington, and also in Livingston, Louisiana. So at the upper left is the signal seen in Hanford. At the upper right, in red, is the Livingston signal, but, well, unfortunately, at least on my screen, you can't, the part of it is blocked on the right. But anyway, the point is that subtracting noise, the 2 detectors saw the same thing, and they detected this gravitational wave arriving on Earth as a very, very slight disturbance in the length of one laser arm compared to the other. So the time for the laser beam to travel up and back in one direction was slightly disturbed from the time to do the same in the other direction. Now, there's something else about how light interacts with a black hole that you know, but that I haven't explained. So I want to take another look. And in this picture, I've drawn a schematic picture where space is drawn from left to right, and time is plotted vertically. And I've drawn the black hole as a black cylinder, which is a sort of a disk in space, but it's there at all times. So it's time independent. And I'm going to draw a light ray in the absence of a black hole as a straight line that goes at a 45-degree angle to the vertical. And units are chosen so that the speed of light corresponds to a 45-degree angle. But a light ray escaping from near a black hole is slowed down. So initially, it's at less than a 45-degree angle to the vertical, but as it escapes, it eventually will propagate to the distant observer at the speed of light at a 45-degree angle to the vertical. But the closer you are to the black hole, the harder it is to escape. So I've plotted the trajectories of a series of light rays, each of which I've chosen to be at least slightly outside the black hole, so they all will eventually escape. But it takes longer and longer before they escape from the black hole and start propagating to the distant observer at a pi/4 angle to the vertical. So here the rightmost one has almost reached the pi/4 angle, and the left second one is closer to that. And the last three that I drew are much farther from reaching that pi/4 angle where they've effectively escaped. As you approach the surface of the black hole, it takes longer and longer for a light ray to escape. And from the interior, not even light can escape. So from the interior of a black hole, even light cannot escape. Nothing can escape, classically at least, according to Einstein's theory, from inside a black hole. Now, I've been showing you a lot of computer simulations of a black hole, but you might ask, could we take a real picture of a black hole rather than these computer simulations? Well, to ask this question, you could first ask, in general, how big should something be at a given distance so we can see it? The fundamental limit comes from the wavelength of light divided by the size of the lens. The angular size of something you can see is given by the ratio of the wavelength of light to the size of the lens. For example, what about your eye as a detector? Visible light has a wavelength of about 1/20,000 centimeters. And your eye, if dark adapted, that means if you're out looking at the sky far from city lights, and it's a very dark sky, there's no moon in the sky, your iris expands as much as possible. Your eye has an aperture of about 1/3 of a centimeter. Taking the ratio, we learn your eye has an angular resolution of about 1/80 degrees. Anything whose angular size is smaller than 1/80th of a degree is indistinguishable to you from a point source, even under ideal conditions. For example, the planet Jupiter, when it's as close as possible to the Earth, has an angular size that actually is about 1/80th of a degree. If it were just a little bigger or closer, or if our eye had a somewhat bigger aperture, we could begin to resolve it with the naked eye, which would mean we could distinguish it from a point source. So the eye can almost resolve Jupiter as a disk, and anything better than the eye can do so, which means that even a very simple telescope, such as the one available to Galileo, was able to resolve the planets as disks. So I gave Jupiter as an example, but Venus, Mars, and Saturn are all almost as equally good. So a very modest improvement on the eye let Galileo see that the planets are not points, but they're disks. But certainly to Galileo and for long afterwards, the stars looked like points. So Galileo could not distinguish the stars from points of light. A simple amateur telescope has a resolving power roughly 25 times better than the naked eye. How much better are the telescopes used by professionals? It's actually a tricky question because it depends on what you want to do. The professionals have telescopes much bigger than a simple amateur telescope, and they can do vastly better for seeing faint objects, but not that much better for resolving objects with a small angular size. In other words, for distinguishing the structure of an object that, Galileo could see the disk of the Jupiter, and even with a simple amateur telescope, you can possibly see bands of light on Jupiter. So, you can see some structure on the planet Jupiter and likewise on Mars. But um, if you want to resolve an object and see that it has structure and observe some of the structure, large telescopes on Earth are not as much better as you might think for resolving structure compared to a simple amateur telescope. The reason is that the atmosphere is a problem. Turbulence of the Earth's atmosphere makes it very difficult, even for big professional observatories, to do a lot better at resolving faint objects compared to amateurs. Now, in modern times, that's less true because there's something called adaptive optics, which has improved what what professionals can do from the ground. But anyway, the turbulence of the Earth's atmosphere is the main reason that space telescopes are important. So it was the reason for launching the Hubble Space Telescope, whose resolving power is more like 250 times that of the naked eye, while a simple amateur telescope was 25 times better than the naked eye. So what if you want to take a picture of a star and directly measure its size by seeing how big it appears to be? Well, the star with the largest appearance size as seen from Earth is Betelgeuse with an angular size of about 1 over 50 million degrees. Way too small even for the Hubble. Betelgeuse is the left shoulder of the constellation Orion. It's one of the easiest and most obvious constellations to see in the Northern Hemisphere, where most of us on this Zoom call are, whether you're in Gaza or Europe or North America. Betelgeuse is the left shoulder, as I said, it's the left shoulder of the constellation Orion. It has the largest apparent size as seen from Earth, but it's not particularly close. It's enormously big. It's one of the largest stars. It's what's called a red supergiant, near the end of its life and exceptionally big. So it's still too small for its size to be directly measured by the Hubble. But there is a way to measure the size of a star. It's called interferometry. Using the wave nature of light, you can combine the signals collected by different telescopes and get a huge resolving power. So here's a picture of Betelgeuse that was taken by an observatory called ALMA in Chile. I'll show you a picture of ALMA in a second. And well, this is what Betelgeuse looked like in the picture. And as you can see, there's a little bit of structure that was seen. There was this whitish spot, and there's a bump on the left in this image, there's a bump on the left of the star. And I'm not sure to what extent amateur astronomers understand the nature of that bump. Here's a picture of the ALMA Observatory, or at least a piece of it. So the ALMA Observatory is a network of radio telescopes. One of them is on the left of this picture. Unfortunately, I can't remember what's hidden, from my view at least, on the right, by my own image and that of the panelists. The picture only shows one of the radio telescopes making up ALMA, but ALMA is a network of these radio telescopes, and the signals from these radio telescopes are combined electronically and made to interfere, to use the jargon. And by looking at the interference pattern, it's possible to achieve a resolving power that no one telescope could achieve. And that was used in building this picture of Betelgeuse. Now, by the way, Betelgeuse was in the news a few years ago as it dimmed markedly and unexpectedly and then recovered. In other words, its brightness recovered. And that was a bit of a mystery to astronomers, and I'm not certain how well it was understood. But it's mostly believed to have occurred because of debris orbiting the star and for some time blocking the view of the star as seen from Earth. Now, I have a question for you. Given that stars have an angular size way below the resolving power of the human eye, why do bright stars look bigger than faint stars? First of all, if you're not sure that the statement is true, then get outside the next time you have the chance when the sky is bright enough that you can see the stars, and you will see that the bright stars look bigger than the faint stars. But the answer, I'm sorry to tell you, has nothing to do with the actual sizes or distances of the stars. It's purely a question of the limitations of the human eye. An ideal point source doesn't look like a point to the eye. The light is spread out, and most of it is near where it should be, but some is spread out more. And the brighter the source is, the more the human eye will see light that's farther from the actual position of the star. So the bright star looks brighter. Oh, sorry, the bright star looks bigger because with more light, the imperfect human eye is seeing farther from the actual position of the star. So um, a star of a given, another way to say what I'm telling you is that to the eye, any star of a given brightness will look the same, regardless of its actual size, because you're not seeing the actual size of the star. The apparent size that you see is determined by the brightness of the star, not by its actual size. That's what it means to say that the eye can't resolve the size of the star. By contrast, here this network of radio telescopes was able to resolve the actual size of the star Betelgeuse, producing this picture, which at least shows a little bit of detail. Now, suppose we want to take a picture not of a star, but of a black hole. Well, we need to ask what are the black holes that have largest apparent size. So I wrote here the largest black holes, but I mean the stars with the largest apparent angular size. The angular size is the physical size divided by the distance from Earth. So among known black holes, the two with the largest apparent size as seen from Earth are the one at the center of the Milky Way and the one at the center of a distant galaxy known as M87. So the one at the center of the Milky Way is 1,000 times closer to Earth, but it's also, by coincidence, approximately 1,000 times smaller. So the apparent size as seen from Earth of these two black holes is approximately the same, even though their physical distances and sizes are completely different. The name M87 is probably not familiar unless you're an amateur astronomer, but it's actually one of the easiest galaxies to observe from Earth. Here's a picture of it taken with, well, I think this is a combination of a picture with an ordinary telescope and a radio telescope picture. And the radio image has been shown in blue to make it easier to see. But the blue is a computer-generated color to help you see what's going on. This is a more modern picture, but astronomers discovered something very strange about this galaxy more than a century ago. Actually, at about the same time that Einstein's theory was being confirmed, although that's a coincidence. So, as seen in the simplest telescopes, the galaxy M87 looks like this bright spot of light with a fuzzy exterior, and naively, that's all you see. But if you look better, and people succeeded in doing this just over a century ago, you see something strange. You see a sort of ray coming out of the central image. It's been shown in blue here, and as I said, I think that this is a radio image superposed on the optical image. But anyway, to highlight the ray, it's been shown in blue in this image. But for a long time, it was a mystery what was the nature of this ray that was coming out of M87. And I mentioned at the beginning of my talk that when people began to take seriously the idea of a black hole, and began to get evidence for it, initially the evidence for black holes was very indirect. And this picture is actually an example, or at least the versions of this picture that existed at the time. There's this strange ray coming out of the galaxy M87, and people began to suspect that there was a black hole at the center, matter orbiting it, spiraling in, generating a lot of energy as it falls into the black hole, and somehow producing this ray that comes out. So, based on a lot of indirect evidence, astronomers began to suspect that this ray, which had been observed coming from M87 for many decades, or originally from about 1920, was being created by a central black hole. The question was, could you actually prove that by taking a picture of what's happening at the center of M87? Well, the black hole in M87, and similarly the one at the center of the Milky Way, has an angular size that's about 1,000 times less than that of Betelgeuse. So to take a picture of it takes an array of telescopes about 1,000 times the size of ALMA. Now, the ALMA array of telescopes is about 10 kilometers across. So here we need an array of telescopes that's roughly 10,000 kilometers across. And a little arithmetic shows we need an array of telescopes working together that's about the size of the Earth. Such an array has actually been constructed. The Event Horizon Telescope, it's called. The first picture of M87 was published in 2019. It actually was world news when it was published, so some of you probably saw it in the news at the time. It remains almost our only photo of a black hole, or more precisely of the environment of the black hole. I say almost because in the 6 years since then, the Event Horizon Telescope has taken a few more pictures, both of the black hole in M87 and of the one at the center of the Milky Way. This is the original picture, and it's a fuzzy picture of the environment of the black hole, but it's the first picture humans were able to take. And what this picture is really showing is the environment of the black hole. The details are complicated. There's matter orbiting the black hole, and it's colliding with itself and falling in, losing, accelerating, radiating, and ultimately producing the light that goes out to us. Very roughly, the black spot in the center is the black hole, and the ring that we're seeing around it is a little bit like the Einstein ring that we had surrounding black holes in other images, but it's more complicated, far more complicated, because the environment of this black hole is very complicated. And the theory of exactly what we're seeing here is quite complicated and not completely understood. But broadly speaking, this is the first picture of the environment of a black hole, showing the black hole in the center and the hot gas around it. So, as I said, roughly the picture shows an Einstein ring created by the black hole in M87. There's a lot more potentially going on. Rotation of the black hole, rotation of the matter, an unknown distribution of matter. So it's hard to understand in full detail what this picture is showing. But it's actually better understood today than it was when the picture was first taken, because there have been refinements of this picture. So a basic question you might ask is, why is the ring brighter at the bottom? That's believed to be because of a combination of the rotation of the black hole and of the matter around it. Now, to get this picture, the astronomers used telescopes in Chile, Arizona, Hawaii, Europe, and the South Pole. So, by combining images from those distant telescopes, they were ultimately able to make this picture using interferometry. Ideally, you'd have physical electronic connections between the telescopes, but that wasn't available. We don't have cables connecting the South Pole to Chile, for example. So they had to store the data at each site, physically move them, and then combine them electronically. And to do that, you had to keep time on each site to much less than the time of oscillation of the light signal you're detecting. So they were detecting roughly gigawave radio signals. So each telescope had to make an absolute recording of the time to better than 10 to the minus 9 seconds. And then the vast amount of data actually from all these different sites was combined electronically and by sort of synthetically creating the interference signal you would have had if the telescopes had been physically combined by electronic cables. They eventually produced that picture. Now there's a planned upgrade with a new telescope in Greenland. Actually, I wrote a planned upgrade, but I'm not sure if it's operational by now. And there are a few other improvements that are possible. You can do a little better by using radio waves of a somewhat shorter wavelength. It's challenging technically, but it's possible in principle. For a big improvement, you could go to space. If you had a radio telescope on the far side of the moon, well, your telescopes would span a few 100,000 kilometers instead of 10,000 kilometers. And if someone really wants to give you the budget, you could have a network of radio telescopes in space and do even better. Well, I hope I've succeeded today to explain some of the exciting ideas about black holes. And I hope there will be better days ahead. And some of you in Gaza will have the opportunity to work in this exciting area, especially to the young people in Gaza. I hope you'll all have better days ahead. And for those who have the interests and the inclination to do so, I hope there will be opportunities for you to join this area or other exciting areas of science. Thank you very much.
Thank you so much, dear Edward. I will now let Pierre, Dr. Pierre and Dr. Arkadas organize the debates. There have been a lot of questions in the Q&A as well as in the chat. Arkadas and Pierre, it's up to you now.
I thank you very much for this wonderful talk. So one question from the audience is, what exactly does one mean by the merging of two black holes? And what is happening to the singularities and the space between the singularities and the event horizon doing such a merger?
Well, when the two black holes merge, the event horizons merge. After after I showed a movie where at the beginning there were two black disks in space. At the end there was one black disk in space. So uh, uh, the final state is well described by the solutions of Einstein's equations that describe a single black hole, as originally found by Schwarzschild and then generalized by Kerr. That's the final state as seen from outside. Part of the question involved what is the geometry inside. It's far more complicated and not particularly well understood. But from an outside observer like us, and we are outside observers, and the LIGO detector detected the outgoing gravitational waves from outside. From an outside observer, after the merger, it simply looks like a single black hole, as described by Schwarzschild and Kerr.
Thank you. Another question from the audience. Can you create a black hole in a lab?
Well, it would be great if we could create a black hole in a lab, but our technology is very, 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 very far away from being able to do that. The closest we come is actually, um, you see, um, there's what's called inertial fusion, where at a national laboratory in the west of the US, at Livermore, I guess, they have two very intense laser beams, or several actually, laser beams that compress a tiny pellet. And the pellet reach temperatures at which fusion occurs. And well, the peaceful goal of the project is to explore the ability to generate fusion. Now, a vastly upscaled version of that experiment, you could imagine collapsing the pellet to a black hole, but unfortunately, it's way, way beyond the range of our technology.
Thank you. Maybe I'll take one more question and then leave to Pierre.
By the way, sorry.
Yeah.
As a physicist, I said unfortunately, because we've got a lot of questions about black holes which are unanswered. They weren't really the topic of today's lecture, but in another lecture, I would have explained what we don't understand. And if we could create a black hole in the lab and watch it evaporate according to the Hawking process, that would give us the chance to explore experimentally some of the things we really don't understand. So as a physicist, I say it's unfortunate we can't make a black hole in the world, in the lab. I can assure you it wouldn't be dangerous. We wouldn't be at risk of being sucked in. Quite the contrary. A black hole created in the lab would actually explode by the Hawking process. But that's another story which wasn't today.
Yeah, yeah. Is space-time the most fundamental physical entity, or could there be other entities that could exist even if space-time didn't exist, and how so?
Okay, the question is space-time as conceived by Einstein the ultimate truth about the universe? Well, it's the best truth we have as of today. But in my arena of string theory, we actually suspect that space-time is what's called emergent from something more fundamental that we don't deeply understand. That again wasn't today's lecture. Actually, I lectured on that in the YMCA building in Ramallah about 30 years ago on a happier occasion. But and the reason I lectured about then was that at that time there had been dramatic progress where the first concrete models of emergent spacetime had been discovered. And on another occasion, I might have lectured today about updating you about developments in that direction, but that wasn't today's lecture. Anyway, we do have very good reasons, I think, to suspect that in some sense space-time is emergent and there's something deeper behind it, but we don't understand what it is. And again, I hope some of the young people on today's call will have better days and have opportunities to join in that research at some point.
Maybe hopefully we'll get that lecture in Gaza. With that, I'll leave to Pierre if you want to continue.
Yes. So first question, do you think there's more to understand about gravitational waves themselves on a fundamental level, or are they only a tool today to study other phenomena?
Well, I think there's still more to do to fundamentally test Einstein's theory of gravitational waves. So it would be nice to be able to see the gravitational wave from a known source. So when LIGO sees gravitational waves from a source whose properties are inferred from what we see, but it's not quite the same as knowing what the source is, calculating the gravitational waves from Einstein's theory and observing it on Earth. So the LISA Space Observatory may be able to do that. So that's an example, but there's more to be done by way of testing Einstein's theory. But beyond that, as you suggest, gravitational waves are certainly a tool for learning more about the universe. Something I see, the LIGO events where the two black holes collide and merge would be completely unknown to us except for the gravitational wave signal. And even the existence, again, something I didn't really explain in the talk was that even the existence of black holes in that mass range was essentially unknown before LIGO. So LIGO has already been a tool for learning new things about the universe that we couldn't tell because we didn't have access to gravitational waves. And I expect more will be learned about the universe by studying gravitational waves. After all, Galileo introduced this study of the universe by light rays, and he didn't learn everything all at once. It's taken centuries, and we're still learning more. So now we've just barely begun the exploration of the universe by gravity waves. And we don't know what we're going to learn as we develop more tools, better questions.
Another question from the audience about black holes. Do we know what kind of matter composes black holes, or if there's a point to the question?
According to Einstein's theory, anything literally can collapse to form a black hole. So Einstein's theory says that a sufficient amount of mass, no matter what it is, tables, chairs, hydrogen gas, anything, if you compress a sufficient amount of mass into a small enough region, it'll collapse to a black hole. And Roger Penrose actually won the Nobel Prize a few years ago for pioneering work he did in the 1960s that gave a precise criterion in Einstein's theory for how much, saying that if you compress mass to a certain extent, it will collapse to a black hole. I've simplified slightly what Penrose proved, but that's the basic idea.
One more question about general relativity. If I'm not mistaken, I think, so you mentioned the link between, or the fact that matter creates curvature in space-time.
Yeah.
And if I'm not mistaken, Einstein never liked this property. When talking about his equation, field equation, he mentioned that it looked like a building. I'm paraphrasing, but it looked like a building where one wing was made of marble. He meant the curvature, while the other was made of poor quality wood, the matter. Do you think he was onto something about this apparent need for source terms and the fact that he did not like them?
Well, Einstein wanted a unified theory that would describe the matter as elegantly as the space-time and curvature. And that is what he was the first physicist to declare that goal. In hindsight, most physicists believe he spent the last 30 years of his life largely in that search. And some of his ideas are interesting today, but some of them are less so. Most physicists today would tell you that the search was premature in Einstein's day because too much was not known about the matter that appears on the right-hand side of Einstein's equations. We know vastly more today than was known in Einstein's day about the right-hand side and what we should be trying to unify with gravity. And of course, it's in string/M theory, that we have had at least some success in getting a glimmer of what Einstein's unified theory might be, though we certainly do not understand it in a way that would have satisfied Einstein.
Arkadas, maybe you want to ask some more questions?
Yeah. A lot of questions from the audience. How are black holes with electrical charge different from regular black holes, and have they ever been observed?
Well, first of all, electric or magnetic charge, soon after Schwarzschild's work, Reisinger and Nordstrom discovered that you could describe a somewhat similar solution. I skipped it in my talk for an electrically or magnetically charged black hole. And no, they haven't been observed. And it's expected that we in practice can't observe electrically. First of all, it's expected that every black hole would have at least some electric charge because it would capture some electrons. There are free electrons in the universe, and the black hole would capture some of them. But it's expected that the electric charge of a black hole in practice would be so small that we wouldn't be able to observe its effects. The reason is that if it were otherwise, the black hole would neutralize itself by attracting protons from the environment. To observe the only hope, in my opinion, would be if magnetically charged black holes had been created in the early universe. Theoretically, that idea makes sense, but there's no evidence for it. So I have very little hope, but there's at least some very slight hope that we could one day observe a magnetically charged black hole.
Mm-hmm. This is maybe slightly technical, but I think it may be interesting to ask. Do you think there's any hope to prove or disprove the weak cosmic censorship conjecture in the near future?
Well, weak cosmic censorship is the statement roughly that if matter collapses, it always produces a black hole rather than something more exotic. So it could have been disproved by computer simulations showing otherwise. But computer simulations of Einstein's equations so far have supported weak cosmic censorship. It's conceivable it could have been disproved by real observations. For example, LIGO could have observed something more exotic, but LIGO's observations seem to be consistent with the idea that the spiraling black hole merged to form a black hole rather than something more exotic. So there are ways weak cosmic censorship, if false, could have been disproved. If it's true, you have to try to prove it. And it's definitely one of the mathematicians working in mathematical relativity definitely aim at proving it, but it's a difficult problem. And like any really difficult unsolved problem in math, there's no telling how long it will take before it's solved. Personally, I spent much of my life hoping that weak cosmic censorship was false, because I thought if a black hole collision would form something more exotic than a black hole, conceivably, the result would eject a lot of energy to the outside in a form we could observe and get, you see, I was asked before, is there something deeper than space-time? If weak cosmic censorship was false, that might have given us a chance to observe the answer to the question. And I was kind of hoping for that. But the fact that both computer simulations, you see, in those days, computer simulations of spiraling black holes weren't possible. I didn't tell this story, but all those movies I showed you only became possible in the 2000s with improvements in techniques for computer simulations. So when the computer simulations became possible, I kind of gave up on hoping that weak cosmic censorship was false. So now the burden is more for the mathematicians to prove it, but that hasn't happened yet. But hope springs eternal.
So there's a video talk of yours on YouTube on light ray singularities and all that. And
Yes.
in there, there's a question about corrections to general relativity by string theory or other other sources of like modified theories, and how such corrections would affect what we know as theorems about black holes, like the singularity theorems and things like that. So you don't give a very concrete answer, but I wondered if in the meantime you thought about this and you have like new answers on that we could.
Well, it's been the answer to your question has been largely pioneered by Raphael Busso, among others. In fact, Busso is someone you might consider inviting for one of these Gaza talks. And there are, well, see, classical general relativity, all the statements are proved. In the quantum case, it's more conjectures, but there's a web of conjectures about what are the quantum versions of the classical statements. I think that's the best answer to your question. So it is believed that in the quantum universe, there are analogs of Penrose's theorems and so on. Incidentally, you mentioned my lecture on light ray singularities and all that, but there's a written version that goes by the same title that I'd recommend to I want to recommend it to physics students who are online. If any of you want to learn the background to Penrose's theorem, for example, it's explained in there.
Yep. Pierre, would you like to continue?
Yes. So I will take two questions in chat, which I will put together. The first one is, does the gravitational radiation you mentioned have any relation with Hawking radiation? And the follow-up is there hope for us to observe Hawking radiation?
Well, first of all, what Hawking radiation is that Hawking discovered that a black hole isn't completely black, but at the quantum level, it has a temperature proportional to Planck's constant h bar, and it radiates. An astrophysical black hole radiates. Okay, the black holes that we know about in astronomy are very big, and they're so big that their Hawking radiation is unobservably small, unfortunately. If there was a miniature black hole, it would have observable Hawking radiation for sure. So one of the questions I was asked was, can we make a black hole in the lab? Well, if we could have, we would also be able to see its Hawking radiation. Because if we could make a black hole in the lab, it would be a tiny one, and its Hawking radiation would be prominent. Not having that technology, the only hope would be if the early universe created black holes so light that their Hawking radiation is detectable. I think they would have to have asteroid-type masses. Well, there's no evidence for it. At best, there's only a faint hope that something like that exists. So in practice, the chance to see Hawking radiation is slim. But there's an analog, there's something that's believed to be very similar to Hawking radiation in concept, which we actually have observed. That's the fluctuations in the cosmic microwave radiation that came from the Big Bang. I'm afraid it's another lecture to explain it properly, but we see little ripples. Okay, we see radiation coming from all directions, but it's not precisely uniform in temperature. And the fluctuations in temperature, we believe, are in effect similar to Hawking radiation. So that's the closest we have to a likely answer to the question.
Since you mentioned a bit,
Sorry, we'll just take a few more questions, and then Edward, you mentioned the possibility of another talk. We will definitely keep you on for that, but I think just a few more questions, and then we'll leave it for today. So Pierre and Arcadas just decide, enfin voilà, opt for a few more questions, and then I think it will be good for today.
Okay.
Thank you.
So maybe a more general question. What draws you to black hole theory and general relativity?
Well, the interface, the relation between, well, first of all, modern physics is largely based on two theories, which are quantum mechanics and Einstein's theory of gravity, general relativity. And making the two work together is one of the main unsolved challenges in physics, and it's quite fascinating. And most of my career has been devoted to different aspects of that. We probe some parts of it using string theory or string/M theory, where we understand how to resolve some of the technical problems with quantum general relativity in the form of string theory. But there's another side of the story, which are conceptual issues involving quantum black holes. So we didn't really get into that today, but that would surround the Hawking radiation and so on. So anyway, to me, the most exciting frontier in physics involves the interface between gravity and quantum mechanics. And although imperfect, our efforts to address that have at least shed a little bit of light on some things. And that's what I've devoted most of my career to.
Arcadas, maybe you have a closing question?
I'll maybe end with one question from the audience. What do you think about testing modified theories of gravity using gravitational waves? Would that be feasible, and how should one approach that sort of thing?
It's semi-feasible. So you can definitely put limits on modified theories. But it's hard to identify a really good target for that work because Einstein's theory is so difficult to modify in a sensible way that really produces observable effects in the lab. So you can sharpen the tests of Einstein's theory, and if they fail, you learn that Einstein's theory needs to be improved in a way that we probably haven't thought of, because we haven't thought of a good way to improve it that would actually modify the predictions that we're able to test with LIGO. So the answer to your question is yes, people can and do test modified theories using gravitational waves up to a certain extent. But nature and the great beauty of Einstein's theory conspire to make it actually very difficult.
Okay, thank you very much. Christine, maybe I'll leave to you.
Yes, thank you so much. Edward, you mentioned the possibility of another talk, and we will definitely take a rain check of that. We have hundreds of witnesses that you agreed to do another talk. Thanks again. I think we will stop here. Remember, this talk is with and for Gaza, and our heart is in Gaza right now, which is being systematically destroyed. Everything is being destroyed, and in particular, the universities and the research labs. So we are with you, Gaza, right now. Edward, thank you so much. Thank you to all of you who attended. Please spread the talk, spread the knowledge about these talks. The next one will be Dr. Michel Mayer, Nobel Prize in Physics, who will be speaking on the 2nd of October on a talk, the title of which I can't remember right now, but I will send it to you all very soon. Thank you for your solidarity. Thank you for your solidarity with Gaza. They need all the help they can get right now. Thanks again. Thank you so much, Edward. Thank you, Pierre. Thank you, Arkadas. We count on you to be respondents for the next talks as well. Edward, thanks again.
Well, thank you for the invitation.
Thank you.
Bye-bye.
Bye.